So last week we discussed the inverse Laplace transform and the standard results of inverse transform. These were the ones from Laplace transform formulae, inverse transform formulae we need to remember. So 1 by s power n is t power n minus 1 by n minus 1 factorial. So one less that we need to remember. Then 1 by s minus a is e power at, and 1 minus s minus a to the power n is e power at t power n minus 1 by n minus 1 factorial. Then 1 by s square plus a square is 1 by a sine at, s by s square plus a square inverse Laplace transform is cos at. Then sine hyperbolic at, so Laplace inverse of 1 upon s square minus a square is 1 by a sine hyperbolic at, then cos hyperbolic at. Then this shifting e power at cos bt. So all these shifting formulas. Then three important ones based on transformation is s by s square plus a square whole square is 1 by 2a t sine at. This is very important. And 1 by s square plus a square whole square is 1 by 2a cube sine at minus at cos at. These have to be remembered. And Laplace inverse of s square minus a square by s square plus a square whole square is t cos at. So these three are very important to be memorized. So of course they are like transformations. We did many problems based on partial fractions and doing that. So of course the properties of inverse Laplace transform, linearity property, this we know what it is. Shifting property, Laplace inverse of f bar of s if it's f of t, then Laplace inverse of f bar of s minus a is e power at into f of t. That was s shifting. If it is t shifting, and Laplace inverse of e power minus as f bar of s is f of t minus a times the unit step function, or what we call as the Heaviside function. So f of t minus a for t greater than a and 0 for t less than a. Now change of scale, Laplace inverse of f bar of as is 1 by a f of t by a. This is change of scale. Okay, multiplication by s means the derivative of the original function. Laplace inverse of f bar of s is f of t. So Laplace inverse of s times f bar of s is the derivative, first derivative of f of t. And multiplying with s power n, f bar of s, taking inverse, is nth derivative of f of t, provided of course at f of 0 these are zeros. F of 0, f dash 0, f nth, n minus first derivative at 0 are all zeros. And then this is true. Now division, multiplication with s is results in differentiation. So division by s results in integration. One time divide by s, we get integral 0 to t f of u du. The Laplace of f of u is f bar of s. So these properties are important. So dividing by s power n will result in integration n times. Now Laplace inverse of derivatives. If it's derivative, it means the original function is multiplied by t. So this is the general formula: minus 1 whole power n t power n f of t gives nth derivative of f bar of s nth derivative of f bar of s with respect to s. So inverse transform leads to this, and on integrals it is division by t. And we discussed convolution theorem, and we did a few problems. We did one problem on convolution theorem. Convolution theorem says Laplace inverse of f bar of s is f of t, and Laplace inverse of g bar of s is g of t. Then the Laplace inverse of the product. So suppose we know the Laplace inverse transform of two functions, then the Laplace inverse transform of the product of the two functions is integral 0 to t f of u into g of t minus u du. Okay, f of u into g of t minus u du, 0 to t. So this is called as the convolution function. We can do this, and we did one example like this question last week. We did using convolution theorem. We ended here. So now we need to proceed further. Some more questions. So this was the second question. More practice we need. So question 3, find the inverse transform find the inverse Laplace transform find the inverse Laplace transform of 1 by s into s square plus a square. So if we go to the properties, multiplication by s results in derivative, but division by s results in integral. So let's see. Now we know that Laplace inverse of 1 by s square plus a square, this is 1 by a sine 80. This is now, so if it is division by s, so this thing is being divided by s, so I get 1 upon s into s square plus a square. So this will be equal to integral of 0 to t this function 1 by a sine 80, or we'll just change the argument or the variable from t to u. You can keep as 80 dt, that doesn't make a difference. So now integrating this we need to do, because sometimes there will be a product of to avoid the confusion between t and the integrating variable sometimes. So now integral of sine is minus cos. So minus cos 80 upon a 0 to t. So this is 1 by a square. Substitute. Okay, so sorry, this will be u. So this will be minus cos 80 minus of cos 0 is 1. So upper limit minus the lower limit. Lower limit for minus cos a u becomes minus cos 0. That becomes minus 1. So we get 1 by a square to 1 minus cos 80. So this is the inverse transform. This is the inverse transform. Let's do another one. Okay. So find the inverse transform of the same 1 upon s into s plus a the whole cube. 1 upon s into s plus a the whole cube. So let us do one by one. Okay. So Laplace inverse of 1 by s cube. Laplace inverse of 1 by s cube is t power 3 minus 1, that is 2 by 2 factorial, that is t square upon 2. So suppose I have s plus a, that is s minus of minus a. Okay. Now this the whole cube. We know that for s minus a, it is e power 80. So what we get here is e power minus 80 t square upon 2. All right. So this is what is Laplace inverse transform of this. So now I divide this by s. That is 1 by s into this is s plus a the whole cube will be integral 0 to t. We get e power minus 80 t square by 2. Okay, so we need to integrate by parts. Half comes out. Now let us integrate by parts. First function we'll take as t square, second function e power 80. So first function into integral of the second. Apply the limits minus integral of derivative of the first 2t into integral of the second. Okay, so let us substitute the limits here. The second limit, if we substitute 0, the whole term will be 0. So we are left with the first limit only. So you get 1 minus 1 by a t square e power 80 after substituting the upper limit. Now this becomes plus 2 upon a integral t e power 80 dt. So you get minus 1 by a t square e power at plus 2 by a first function to integral of the second minus integral of derivative of the first into integral of the second. So when you multiply, we get minus 1 by 2a t square e power at plus. Now let's look here. 2 by a multiplied by half gives 1 by a, and that 1 by a multiplied by this minus 1 by a, we'll get minus 1 by a square t e power minus at. Sorry, this is minus. Now this minus into minus is plus, so plus 1 by a into plus 1 by a, 1 by a square into integral of e power minus at will again be this. Apply the limits. So minus 1 by 2a t square e power minus at minus 1 by a square t e power minus at minus 1 by a cube into e power minus at minus e power 0, 1. So let us take 1 by at common. Sorry, 1 by a cube common. Minus into minus becomes plus, so plus 1. Then this is minus e power minus at. Then multiplying with a, we get minus at e power minus at. Then minus a square by 2, a square t square by 2 e power minus 8. So this is the inverse Laplace transform of this function. So concept of Laplace was very simple. Just we needed to be careful in the integration. That's all. In fact, directly you can write the successive integration formula. Keep differentiating the first function, keep integrating the second function, and keep alternating the positive and negative signs in the integral for each term. You will get the same thing. All right. Next question. We'll do a little more involved. So find the Laplace inverse of s plus 2. Okay, and s square plus 4s plus 5 the whole square. So let us find this. This we can write as Laplace inverse of s plus 2 s plus 2 the whole square, s square plus 4s plus 4 plus 1. So that becomes s plus 2 whole square plus 1 square whole square. Now, so we need to find this. Okay, this is the required. So we can start with Laplace inverse of s by s square plus a square whole square. This is one of the um, 13 that 15 formulae. Laplace inverse of s upon s square plus a square the whole square is 1 upon 2a t sine 80. We need to use this result. So when we use this result, so you get 1 upon 2 into 1a into t sine 80, that is 1 into t. So therefore Laplace inverse of s plus 2 into s plus 2 the whole square plus 1 square the whole square will be e power minus 2t. A is minus 2. Here s plus s minus a. So s minus of minus 2. So e power minus 2t into half t sine t. All right. The last one. The last one. After that, we'll do applications on differential equations. So if f bar of s is log of s plus 1 by s minus 1. Okay, find Laplace inverse of f bar of s. What can we conclude here? What observation? See, we know the Laplace inverses of s plus 1 and 1 by s plus 1 and 1 by s minus 1. But here it is log. Very clearly log means integral. Okay. So see this. Consider this one. F bar of s is log of s plus 1 minus log of s minus 1, which is nothing but integral of 1 by s plus 1 minus 1 by s minus 1 or okay. So ds Or in other words, derivative of this d by ds of f bar s is 1 by s plus 1 minus 1 by s minus 1. Now, Laplace inverse of the derivative is Laplace inverse of this is e power minus t minus e power t. This is what it is. So now derivative will lead to, so let's look at the results. Yeah, derivative of f bar of s, okay, is minus of, if this is if Laplace inverse of f bar of s is f of t, then this is the case, minus 1 to the power n t power n f of t. So yeah, so now this is minus 1 to the power 1 t f of t is equal to e power minus t, where Laplace inverse of f bar of s is equal to f of t, which implies f of t multiply with a minus sign, this minus 1 on e power t minus e power minus t upon t, which can be multiply and divide by 2. So 2 by t, e power t minus e power minus t by 2 is sine hyperbolic t. So this is the inverse transform of f bar of s. We want inverse of f bar. So if we equate this to f of t, okay, the derivative of f bar of s are standard ones. So on the left hand side can be written as minus 1 to the power 1 t f of t, and we find out the Laplace inverse on the right hand side. Then from there we can find t. So this is the trick. So this chapter, like the chapter on integrals, requires a lot of practice. That's all. Without practice, this although it is very easy and scoring, this appears to be very difficult if we don't practice and remember the formula and how to apply the formula. Now, whole idea of Laplace transforms and Laplace inverse transforms, why do we need such transformation, is to solve linear differential equations. So solving linear differential equations using Laplace transform. So directly we'll go to examples or problems. So solve. So d cube y by dx cube plus 2 d square y by dx square minus dy by dx all right, either in terms of x or in terms of t. So we'll do both, one problem this way, other problem that way. Minus 2y equal to 0. So this is a linear differential equation. Now the given LDE, we will write an sure y triple dash plus 2y double dash minus y dash minus 2y equal to 0. Apply taking Laplace on both sides. So applying Laplace transform on both sides. Applying Laplace transform on both sides. Okay. So we get Laplace transform of the third derivative, then okay, I have to give the given conditions. I'll just do that. Laplace transform of the second derivative minus Laplace transform of the first derivative minus 2 times Laplace transform of y. Okay, here the condition, given conditions, y of 0 is 0, y dash 0 is 0, y double dash 0 is 6. Okay. Now let us go back to Laplace transforms the formula, the second set on derivatives that we did. Yes. So Laplace transform on derivatives. If we remember this, for differential equations, Laplace transform on derivatives, that is very important, especially this one, the most general one. Laplace transform of f, this is nth derivative. This is not f power n, it is nth derivative of t is s power n f bar s minus s minus s to the power n minus 1 f of 0, s to the minus s to the power n minus 2 f dash 0 minus s to the power n minus 3 f double dash 0 and so on. So we will use this here for each case. This is very important. So this will imply the first term, Laplace transform of third derivative, will be s cube into, let Laplace transform of y be y bar, just like Laplace transform of f. So let, okay, where Laplace transform of y is y bar of s. So y bar of s minus 1 power down s square into y dash 0 minus s No, sorry, the first one is y of 0. Second one is s into y dash 0 minus 1 into y of 0. So start with the highest term. The first term is fixed s cube y bar s. Keep reducing the powers of s. And next terms start with y of 0, then y dash 0, then y double dash 0. So, okay. So this is the first step. This is the first part. Laplace of third derivative of y. Then plus twice of Laplace of second derivative of y. Let us start. This will be s square into y bar s minus s into y of 0 minus 1 into y dash 0. The next term minus of s into y bar s minus s bar 0 into y of 0. And the last is 2y bar. All right, so now this is equal to 0. Applying all terms, we know that y of 0 and y dash 0 are zeros. So this is given to be zeros. This one, this one, this one, this one, this one. They're all zeros. Y double dash 0 is 6. So this is 6. So simplified version, you get s cube into y bar s minus 6 plus 2s square into y bar s minus s y bar s minus 2y bar s is equal to 0. So what we get, take 6 to the other side, y bar s will be 6 upon s cube plus 2s square minus s minus 2. So this is y bar of s. So what will be y? The whole purpose of solving differential equation is to find y. So we have, Laplace transform of y is y bar of s. So y is Laplace inverse of y bar of s. So we just have to find the Laplace inverse of this. So just see how a differential equation, solution of differential equation, has converted to just a linear algebraic problem. There is no integration that we have used so far. Integration is only in finding the Laplace inverse, but there is no integration. If you remember the linear differential equation solutions, what we did, we first need to find the auxiliary equation and find the roots of the auxiliary equation. From that, you find the complementary solution, complementary function. And of course, right hand side is 0. So there's a homogeneous equation. So we don't have a particular integral. So complementary function we find and we solve. But see the same thing here. We get exactly the same thing. Now let us look at solving this. If you, by inspection, you see this is s cube, this is 2s square, this is minus s and minus 2. Let us see by inspection which value of s satisfies this equation. So what we get, s cube plus 2s square minus s minus 2. If I substitute s equal to 1, I get 1 plus 2, 3. 1 plus 2 is 3. Minus 1 minus 2. 3 minus 3 is 0. So s equal to 1 satisfies the equation, which means s minus 1 is a factor. Now s minus 1, s square, now I have to factorize. So s cube term, you see, s into s square gives s cube. The constant term we have to see, minus 1 into what will give minus 2? Minus 1 into 2 will give minus 2. Now the middle term we require. To find the middle term, you cross check. The coefficient of s square is 2. So here we have minus s square. To get plus s square, we will have to do 2. No, to get 2s square, we'll have to add 3s. So now we can see here s cube minus s square plus 3s square will give us 2s square. Then 2s minus 3s will give us minus s minus 2. So we have factorized. Now this is a standard factor. We can factorize this as s plus 1 into s plus 2. So we have factorized this. So y bar of s is 6 upon s minus 1 into s plus 1 into s plus 2. So this can be resolved into partial fractions. These are linear factors. So we get 6 times of 6 is equal to a times s plus 1 s plus 2 b times s minus 1 into s plus 2, equating the numerator on both sides, plus c times s minus 1 into s plus 1. So put s equal to 1. Put s equal to 1. Right hand side 6. A into 1 plus 1, 2 into 1 plus 2 is 3 times 0 plus 0. S minus 1 becomes 0. So we get A is equal to 6 upon 6. A is 1. Next put S is equal to minus 1 to get B. So what happens? 6 A times 0 plus B times minus 1 is minus 2. Minus 1 plus 2 is plus 1 plus C times 0. When you put S equal to minus 1, you get 0. So B we get as minus 3. 6 divided by minus 2. Next put S is equal to minus 2 to get C. 6 is equal to A times 0 plus B times 0 plus C times minus 2 minus 1 is minus 3. Minus 2 plus 1 is minus 1. So What do we get? This is plus 3. C is 6 by 3 is 2. Therefore, y bar of S is 1 A upon S minus 1 plus B upon S plus 1. So minus 3 upon S plus 1 plus C upon 2 upon S plus 2. So y, now this is a function of x originally. If it is a function of t with time, then uh, you have to write in terms of t. Otherwise, the y of x is Laplace inverse of y bar of s. This is easy. Laplace inverse of s minus 1 is e power t minus 3 times Laplace inverse of 1 by s plus 1 is e power minus t plus 2 times Laplace inverse of s 1 by s plus 2 is e power minus 2t. So this is, I'll write as x here because we are function of x. So x minus x minus 2x. So this gives the function. So this is how we use Laplace transform to solve the differential equation. We may wonder why, see, these are involved steps apparently, but this becomes a linear algebraic equation straight. And for converting big problems, this is easy if we know procedures of converting, inverse to inverse transform. There are, otherwise, suppose next problem we will do, suppose there's a particular integral, then we have to remember both. If it's a non-homogeneous equation, we have to find the particular integral also. But using Laplace transforms, we can do this problem much easily. Let's take example 2. Okay, in terms of t, this is a function of x. So solve x double dot, that means second derivative with respect to time, minus 2x dot plus x is equal to e power t, where at t equal to 0, x is equal to 2 and x dot is minus 1. Now let's look at the solution. So the given linear differential equation, x double dot minus 2x dot plus x is equal to, let Laplace transform of x of t be x bar of s. Therefore, Laplace inverse of x bar of s is x of t. We want to find the function of x in terms of t. So instead of y, we have x now. X is the dependent variable, t is the independent variable. Okay, so applying Laplace transform on both sides of the LD. So we get this. So this is second derivative. So what we get is, we get s square times x bar of s, Laplace transform of the derivative, minus s times function at 0 minus 1 with first derivative at 0 plus minus 2 times s into x bar of s minus s bar 0 1 times x of x at 0 plus Laplace transform of x is s bar of s. Now Laplace transform of e power t. E power t. This is a function now. Is 1 by s minus 1. Laplace transform of e power at is 1 by s minus a. So we get this. So now let us apply the boundary conditions. So y of 0 is x of 0 is 2, x dot 0 is minus 1. So this is what we need to apply here. So we get s square minus, this is s into 2. X of 0 is 2 and x dot is minus 1. Minus of minus 1 becomes plus 1. Minus 2 times s into s x bar s minus x of 0 is 2. So collecting x bar s terms, you get s square we get s square minus 2s plus 1. Okay, then we have other terms other than x bar. You have minus 2s, this is plus 1 plus 4, so plus 5. So first we need to simplify this. This is s minus 1 the whole square into x bar of s is 2s minus 5 plus 1 by s minus 1. Okay, x bar of s divided by s minus 1 whole square. So instead of doing the writing into a single fraction and doing partial fractions, we'll directly simplify here like this. In the denominator, the first term 2s minus 5, I will write as 2 into s minus 1 minus 3. Okay, so this is 2s minus 5 divided by s minus 1 whole square plus 1 by s minus 1 divided by s minus 1 whole square. That becomes 1 by s minus 1 whole cube. So we get x bar of s is 2 upon s minus 1 minus 3 upon s minus 1 the whole square plus 1 upon s minus 1 the whole cube. Therefore, x of t is Laplace inverse of x bar of s, which is Laplace inverse of 2 by s minus 1 gives 2e power t. Now this is minus 3 times e power t into t to the power 2 minus 1, that is 1 by 1 factorial, plus Laplace inverse of this is e power t into t to the power 3 minus 1, 2 by 2 factorial. So x of t, we can take e power t common. And okay, 2 steps we will do. We get t square by 2 minus 3t plus 2. So this is the function. Take half outside. T square minus 6t plus 4. This is the solution of the differential equation. We did not find the complementary function. We did not find the particular integral. Directly we did this. First do Laplace transform and then find the Laplace inverse. So why do we need to learn Laplace transforms is to apply in differential equations. Okay, linear differential equations especially. One more. Okay. Solve again d square x upon dt square plus 9x is equal to cos 2t if x of 0 is 1 and x of pi by 2 is equal to minus 1. So here, interestingly, look at the given conditions. The first derivative is not given, and that is what is usually very important in when we do Laplace transform of the differential equation. So the first derivative is not given, but two conditions are given of the function at t equal to 0 and t equal to pi by 2. So let us take let x dot 0 be equal to a. That means the first derivative of t, first derivative of x with respect to t at t equal to 0 is a. So let's begin. So given LDE is just x double dot t plus 9x of t is equal to cos 2t. So let x dot equal to a and Laplace transform of x of t be equal to x bar s. This we should write always. So now applying Laplace, linear differential equation, you get Laplace of x double dot t plus 9 Laplace of x bar t, Laplace of cos 2t. So this gives us s square x bar of s minus s x of 0, this is known to us, minus x dot 0, this is unknown to us, plus 9 times x bar of s. Right hand side is s upon s square plus 2 square. So this boils down to s square plus 9 times x bar of s minus x of 0 is 1. So this is 1. So I get minus s, and I have taken this as a. So let's take this to the other side. So s square plus 9 times x bar of s is s plus a plus s by s square plus 4. So let's simplify. So x bar of s is s upon s square plus 9. This is a standard cos 3t, plus a by s square plus 9. This is a standard. It will be sine 3t we'll get. The last term only is so this we'll have to use a little trick. Hmm. Mm, mm. Because s by 9 factor is there, I think this can simplify further. We will do this simplification. Okay, the last part, we'll do simplification like this. I 9 minus 4 is 5. So I multiply and divide by 5. Numerator, I will write as s square plus 9 minus s square plus 4. So 9 minus 4 is 5. 5 cancel. So s by s square plus 9 plus a by s square plus 9 plus, let us see, s by 5 s square plus 4 minus s by 5 s square plus 9. So this term and this term we can add, bring it to a single term. So 5 minus 1, so I'll get 4 upon 5 s by s square plus 9 then plus a by s square plus 9 plus 1 by 5 into s by s square plus 4. So therefore Laplace x of t, Laplace inverse of this. Now first term is a standard Laplace inverse. We apply Laplace inverse now. This is s by s square plus 9. We get this as cos 3t. Next term plus a upon 3 sine 3t. Okay, plus, now look at this. This is s by s square plus 4, 1 by 5 cos 2t. So we get this as x of t. Only thing, a is unknown. One more condition we have to use, which we have not used, is the value of x at pi by 2 is -1. So now x at pi by 2 is equal to -1. So we get, substitute 4 by 5 cos of 3 pi by 2. Cos is 0 at odd multiples of pi by 2. 90, 270, so on. So 4 by 5 times cos 3 pi by 2 is 0, plus a by 3 sine 3 pi by 2. Sine pi by 2 is 1, sine 3 pi by 2 is -1, plus 1 upon 5 cos pi 2t, right? T is pi by 2. 2t will be pi. Cos pi is -1, is equal to -1. So we get minus a upon 3 is -1 plus this 1 upon 5, which is -4 upon 5. So which gives a is equal to 12 upon 5. So now we get the substitute a is 12 upon 5 here, and 12 upon 5 divided by 3. So you get 4 upon 5. This term a by 3 is 4 upon 5. So therefore x of t is 4 by 5 cos 3t plus 4 by 5 sine 3t plus 1 by 5 cos 2t. Now if we observe the differential equation, right hand side is cos 2t and we have got cos 2t here. So this is our particular integral. This will be our complementary function for the homogeneous part of the solution of the homogeneous part of the differential equation. So here we see we did not do any of those methods of solving the linear differential equation. Just 2 steps: apply Laplace transform, find y bar of s or x bar of s, and then do the inverse Laplace transform. That's it, and we get the solution. What if the function is not linear differential equation with constant coefficients? How will that change? We will do one problem on that. Solve. T times y double dash plus 2y dash plus t times y is equal to cos t. Now first derivative is also not mentioned. Just a sec. Let's mention to be okay. Given y of 0 is equal to 1, only one condition given. So note the above is not linear differential equation with constant coefficients. So it is a linear differential equation without constant coefficients. So we have, method of variation of parameters, method of undetermined uh, coefficients, and so on. However, this will be, those are standard undetermined coefficients work for only constant coefficient. Only thing that will work is method of variation of parameters. And that too, we have cos t on the right side. This becomes a very difficult integral to solve. A difficult differential equation to solve. But if we use Laplace transforms, it works very well. Let us see this. Okay. Now, so let Laplace transform of y of t be y bar of s. Okay. Now, applying Laplace to both sides. Now, see, let Laplace transform of y double dash t. We know it is a function in s, right? We will write this as some, I will not write the standard f, I will write some f bar of s. Then note that if Laplace transform of the second derivative is f bar of s, then Laplace transform of t multiplied by this one. Whenever we multiply with t, what will it give? Minus 1 to the power n, that is 1, d by ds of the Laplace transform. Okay. So this is what is important. So let us do this now. So applying Laplace transform I'll write LT for short. Applying Laplace transform on both sides of the linear differential equation. We get Laplace transform of t y bar, y double dash, plus 2 times Laplace transform of y dash plus Laplace transform of t times y is Laplace transform of cos t. This will be minus d by ds, this result of Laplace transform of y bar, y double dash. This is the change. Plus, okay, this is 2 times Laplace transform of y dash. I'm not changing that. This will again be minus d by ds of Laplace transform of y, because there's a multiplication with t. So this is the key step of this problem. Okay, this is the key step, because here in the equation there was multiplication with t. Now if there was t square or t cube, then the derivative will be twice, thrice, so on. That's what. So now this is minus d by ds times Laplace transform of second derivative is s square y bar s minus s into y of 0 minus 1 into y double dash 0. Now y double dash, not double dash, single dash 0. This is already double dash, so first derivative. Plus this is 2 times s into y bar of s, this term, Laplace transform of y dash, minus y of 0. Now this is minus d by ds of y bar s. So let us find this now. And right hand side is s by s square plus 1 square. Now let us see. Y of 0 is 1. And y dash 0 will be some constant. But when you differentiate, this term goes away. So let's differentiate partially with differentiate this with respect to s. And this is 1. So, okay, this is 1. This is some constant. Apply the derivative now. So minus of, okay, I'll write, you can directly write, but I'm just writing terms here so that you don't, this is 1. So derivative of s with respect to s, you will get plus 0. Here we get 2s y bar s. Y of 0 is 1, so minus 2. Minus, we just get dy bar by ds. Writing this, differentiating by UV rule, product rule. First function integral keep the first function, differentiate the second, dy by ds. Differentiate the first, keeping the other as it is. So this is 1 plus 0 plus 2s y bar of s minus 2 minus dy bar by ds. Now if you look at this term cancels. Then we have collect this and this term. We get minus of s square plus 1 dy bar by ds. And we have this as 1 minus 2, that is minus 1. Take it to the other side, it becomes plus 1. Now dividing by s square plus 1 with a minus sign. So we get minus 1 upon s square plus 1 minus s upon s square plus 1 the whole square. So this is t sine t. So now Laplace of the derivative, Laplace inverse, we have to do this. The same result we need to apply here. T times y gives derivative of the Laplace transform. So here, since Laplace transform of t times y is minus d by ds of Laplace transform of y. Laplace transform of y, that is y bar. So this gives us, this is minus Laplace transform of t times y. We'll get y straight. So remove the minus sign. Minus multiplied by minus 1 throughout, you'll get plus. And then t times y is Laplace inverse of 1 by s square plus 1 plus Laplace inverse of s by s square plus 1 the whole square. So t upon y, t into y is, this is sine t, and this one is 1 upon 2a t sine at. So t sine t. Okay, so let us now divide by t. So y of t we get as sine t upon t plus half sine t. This is the function. This would have been very difficult to solve if it was the other method. Okay, so this, of course, here. So this, if we write here, it will be useful, because again we are converting back to that. So this is the way we find the solution. All right. We can do more problems, but I think I'll stop here. There's no point starting a new topic in another just 10 minutes. So I'll stop here. With this, we complete the applications of Laplace transform. Of course, what we could do, uh, the next topic, very important topic, is partial differential equations. And of course, there are short topic of application of differential equations, orthogonal trajectories, and the general verbal problems, application problems. So that we'll take up. So today's class we end here. So we just need to practice. I'll share with you as an exercise the problems from the previous gate questions. I will upload them in Moodle. So I'll do that. So please note that till last class I have uploaded the recording in Moodle. So you can have access to all the classes till the last week. So today's I'll try to do today, or otherwise latest by tomorrow I'll do that.